TV at home, so when I watch your YouTube videos, you're humongous.
It's like, damn, it's big, isn't it?
Okay, so we're gonna talk about Breakpoint Chlorination. We shot that video the other day when we went through the study guide. And just for the viewers, study guides are coming. They're gonna be available on my website. They're very, very informative. I spent a lot of time doing the research, double check, triple check. They'll be available. My coworkers get the study guides and they help me make sure that they're fine-tuned and ready to go. So we're gonna talk about Breakpoint Chlorination. And let's see, pen, black, good. All right, so let me just say this first before we really get going in this. There it is. I need this. We'll go back to that in a minute. So, Breakpoint Chlorination. On your certification exams, you're going to get questions that are going to say something like the free chlorine residual let's try that again. The free residual is probably, let's call it 3.2 milligrams per liter. The dose, the chlorine dose, is, let's just say it's 4.8 milligrams per liter. And the question is going to be, what is the demand? Okay, so demand equals dose minus residual. Because we know how much we're dosing, and we can take a residual, and it could be free, it could be total, doesn't matter. This equation works because if we, like I said, we know the dose, we know the residual, and we always dose more than the residual is going to be. And we're just now starting the conversation in this video series about dose, demand, residual, how much chlorine, or how the chlorine interacts with the water, the raw water. So we're going to go into breakpoint chlorination here in a moment, but we have residuals that we could, there's 3 different types of residuals: free, total, and combined. So, and I'll go ahead and write that down right here. There's free, total, and combined. Now, just a real quick explanation. When we first start dosing our water with chlorine, if there's ammonia present in the water and other organic substances, the chlorine, the way it acts is first, it combines with those organic substances and creates what we call a chloramine. A chloramine is also known as a what is the term? I'm messing up so big right now. Let's stop this and start over. I'm sorry, guys. I had it. Breakpoint chlorination. Before we get into that, let's just go over some of the terms that we're going to use. Now, when we dose the water with chlorine, the initial reaction is going to be that chlorine is going to interact with metals that are in the water and oxidize them. But then if there's any ammonia or organics in the water, chlorine is going to interact with that. It's going to start combining with those organic materials, especially ammonia, to produce chloramines. So let's write it like this. Chlorine plus ammonia equals chloramines. Chloramines are also known as chlor-organics. Okay, so what we call these, they're called chloramines. They're also called chlor-organics. But when we test to see what the amount of chloramines is in our water, we call that, we're going to call this combined residual. I have to remember to pick this pen up. A combined residual is the amount of chlorine that is combined with this ammonia and this other organic material to form chloramines. Now, we don't have a combined residual test, but we do have a few others. We have what we call total chlorine, residual, and we have free. And we have two different tests that we can do in the field. Testing for chlorine residuals can be done in the lab through a titration method that gets a color, they match it up. In the field, we have test kits. And the test kits come with a little packet of reagent. They have reagent for total chlorine and reagent for free chlorine. Comes with a chlorometer, or a colorimeter, excuse me, which when we take the sample, we put it in the meter, we calibrate it, zero it out when the water's clear, with the original sample. Once the meter's calibrated, we will take the sample, we'll add a packet of reagent, give it some slight mixing, give it a moment to react, depending on the test that we're doing. Put it back in the meter and test it. And what it's doing is it's sending a little beam of light into the sample cell that contains the water with the reagent that has turned a certain color, and the meter will tell you what the residual is. Just takes a moment. Now, free chlorine is chlorine gas. Chlorine gas available in the water. It's also known as the free available chlorine, because if we have free available chlorine in the water and we're practicing breakpoint chlorination, then that chlorine is available in case the water interacts with something. If something pops up, that there's something that wasn't quite there as in the initial disinfection phase, the chlorine will react with it, neutralize it, kill it. That's what we're hoping for. Total chlorine is the combination of free chlorine and combined chlorine. Because we don't test for combined chlorine, what we do is we will take a total chlorine residual, we'll sample that, we'll get our total chlorine number, and let's say that total chlorine is 5.1 milligrams per liter total. But we get a free chlorine residual of 3. that is gonna leave us.
Yeah, good luck. Let me know how it works. See you, man.
So here's the total chlorine. Here's the free chlorine. The difference after we subtract it is 2.1 milligrams per liter, and that would be the combined residual. That would be how much of the total amount is combined chlorine. That's the chloramine level that's in the water. Okay? So now that we've talked about residual and how that initially takes place, let's take this, move that out of the way. And we will talk about breakpoint chlorination. Now, over here on this side, we have residual. Whoops. Yeah, what the heck. Over here, we have the dose. So along this x-axis, we're doing dose. Along this y-axis, we're doing residuals. What does that mean? Well, what we want to do when we're disinfecting water is we want to add chlorine. We want to add chlorine to the water, and then we want to give it 20 minutes to interact with everything in the water it wants to react with. And chlorine wants to react with everything. Chlorine's a bully. Chlorine's a killer. Chlorine is a destroyer. That's how chlorine acts, and that's what we want because it's very, very effective at very small doses. Okay? Which is one of the advantages of using chlorine. If you know what you're doing, you can do it safely, you can deliver it safely, handle it safely, dose the water with just enough to do the job. That's one of the jobs of an operator, right, is to be efficient. Our first job is to protect the health and safety of the public. Number one, that's our first job. Our second job as an operator is to be efficient. Efficiency means, especially when you're dosing chemicals into the water for treatment or disinfection, is you want to dose enough of the chemical into the water that it does the job. If you dose too little, why dose at all? You're not doing the job. If you dose too much, you're wasting money. And that money belongs to our ratepayer. We're responsible for making sure the ratepayer is not overpaying for treatment that doesn't need to be done. If you're efficient, then you're dosing in enough chlorine to make sure that the water is safe. Okay? And these limits are at a minimum throughout and to the furthest point in the distribution system. We want a minimum 0.2 milligram per liter, and this would be a free chlorine residual. The MCL, the maximum contaminant level for chlorine, is 4 milligrams per liter. So now, the first initial dose of chlorine here is going to go into the water. I want red. I want you to go away. It's going to go here, and initially there's going to be no residual. So we're dosing with chlorine, and then we wait 20 minutes and measure with residual. The reason why is because once you dose with chlorine, you want to give it 20 minutes to interact with everything it wants to interact with. I was just saying this before, I'm repeating myself, but it's important information for everybody to understand. We give it that 20 minutes. and then we measure a residual. We want to see what it did, what that dose did. So we start here, we start dosing, and initially you get no residual. In fact, you start dosing and you keep increasing the dosing, and it goes like this. I do that better on a real whiteboard, but the reason why you don't get a residual here after 20 minutes is because these are, at this dose or at this initial phase of disinfection, the chlorine is breaking down and oxidizing metals. Metals like iron, manganese. It's even breaking down nitrate, right? So if there's nitrates in the water, it's trying to break that down first. So the chlorine, the entire dose of chlorine is getting used up right away. It's also doing all the other things that we want it to do. It's starting to combine and break down organics. Now, as we increase the dose over time, we're going to start seeing a residual. And what we're measuring here is what we call total residual. We use green. So through this part right here, we're going to call this A. We're measuring for a total chlorine residual. What's happening here is chlorine, as we increase the dose, chlorine is reacting with the ammonia, those organic compounds in the water, to form chloramines. Those are the combined chlorines that we were talking about. Okay, so as we increase the dose over time and we measure the residual, we're going to see that residual climb. It's going to climb up to this point right here, the peak. Okay? And again, as it climbs up and it's going to level out right here, we're still increasing the dose as we go. As we increase the dose of chlorine, the chlorine starts to break down these chloramines. Now the chloramines getting formed here are called monochloramines, meaning one atom of chlorine. Dichloramines, I'm not going to spell it all out. Dichloramines, and I'll just make it like this so it stands out better. Dichloramines, and then trichloramines. So through this part A right here, this A part of the curve, we have mostly monochloramines, but we also have dichloramines and trichloramines. These are weak disinfectants, but they're long-lived. It takes 10 parts chlorine. So let's say this, it takes 10 milligrams per liter of chlorine to oxidize or destroy 1 milligram per liter of ammonia. So it takes a lot more chlorine to break down a little bit of ammonia, or these organic compounds that are in the water. This is when chloramines are formed, but we increase the dose of chlorine again. And what that does is now we have enough chlorine that it's breaking down. Let's change the color here to, let's call it purple. Yeah, do that. So in this part of the curve, and we're going to call that B. Now we are destroying chloramines. And that's why the total residual starts to drop, is because now the chlorine is destroying all of these chloramines. It's trying to destroy them all. So this is destruction, or I'm just gonna call it destruction of chloramines down that part of the curve. Now, we want to, right in this area is where we want to start testing for free chlorine residual, because again, we're increasing the dose. We're giving it contact time, okay? We're increasing the dose, we're giving it contact time, and right at this point, which we call breakpoint, is when we start producing a free chlorine residual. But we don't know it yet. We don't know that we hit breakpoint yet. We won't know that we hit breakpoint until we dose again. And when we dose again and the residual goes up, we'll just say right there, if the free chlorine residual appears and it increases with each dose at the same, the residual rises at the same rate as the dose, then we know we've achieved breakpoint. It's kind of the definition of breakpoint chlorination. You've achieved breakpoint when with every increase in dose, you have a corresponding increase in the free chlorine residual. And we're taking notes. We're tracking this, right? We're tracking time and how much was dosed and what the residuals are. We're tracking that all along the way. So like I said, when we hit breakpoint, you're not going to know that. You're not going to know that until after you've increased the dose here, and then you increase the dose again. You're going to see, hey, wait a minute, it's starting to increase the same as the dose, that at the same rate I've increased the dose. Now the interesting thing here too is, and let's go to highlighter in yellow, go away. So at this point, at the break point, you're going to see that there is a combined residual. Pink, all right, go away. So this combined residual with chloramines that was formed over here, it's going to continue right through here. It's going to stay where that break point is. So you're going to, as long as the raw water that you're disinfecting, as long as the quality stays the same, your combined residual is going to stay the same. Okay, so it's important to understand that once we've achieved breakpoint, we're going to determine how much free chlorine residual we want to send out into the distribution system. Because we have these min-max, right? And we don't want to send out, depends on the system. Here in our system, we don't want to send out 4 milligrams per liter. It's way too much chlorine. We want to be efficient. We don't want to over chlorinate the water. So we have a different dose that we do, and we've learned what that is over time. We've achieved breakpoint, we maintain a certain residual, and as long as we maintain that, we're good. I mean, we have somebody that goes out in the system every day who pulls samples that go into the lab, and while she's pulling samples, she's testing for residuals, and she's marking that down in her logbook. This is important information to keep. And people look at that information and say, all right, we're maintaining these residuals. Things change over time, temperature changes. the water quality might change. And it might just be slight, but over time we get to see those changes and what's going on. So, getting back to this, once we achieve breakpoint, as far as the raw water quality or characteristics remain the same, we're gonna have a breakpoint, or we're gonna have a combined chlorine residual here. Again, we don't have a test for combined residual that we do in the field. So what we do is we take a total, get back to this right here, that'll be the pen. So what we're gonna do here in this area is we're going to take a total chlorine residual, we're gonna do a test for total, and we're gonna test for free. Once we've done that, we're gonna subtract free from the total, and that's gonna give us the combined residual. So now we know, out of this, now we know how much is free and what is combined. These chloramines, as I was saying earlier, it's a weak disinfectant, but they last a long time. We don't mind having those in the distribution going out there and interacting with anything that it wants to oxidize, to reduce it, kill it, destroy it, those types of things. All right? Any questions? Everybody good? So now that we've achieved breakpoint, we're operating our system within the guidelines that we have within our discharge permit. Let's talk about another way of disinfection. It's called chloramination. I'm gonna write it right here. Chloramination. Chlorine. What we're doing in chloramination is we are using these chloramines, especially monochloramines. This is ideal because these are the most long-lived. We're using these chloramines and we're going to send them out to the distribution system, and that's going to be the way that we keep our water safe out in the distribution system. How do we achieve chloramination? Well, it's different than breakpoint. A system can't use breakpoint in the morning and then switch over to chloramination at night. That's not the way it works. You're either practicing breakpoint chlorination or chloramination. And what happens is you'll go through the same process, increase the dose incrementally every 20 minutes or so until you achieve breakpoint and just past that. And then in a system that's chloraminating, at this point, they're going to start injecting ammonia into the water. Now remember, over here we had ammonia and we formed these chloramines, and then we destroyed them, achieved breakpoint. There's still some chloramines left, and now we have a free chlorine residual. But when you're chloraminating, when that's the way you're practicing your disinfection, you add ammonia and you bring, what you're doing is you're going past the breakpoint, right? You're reducing your free chlorine, you eliminate free chlorine, and then you come up to this point. You want to be right in this area, predominantly with monochloramines, and this is where you want to maintain that level of total chlorine residual. And we're going to continue to test throughout the system and at the plant and all that, because we want to stay right there at the B, at this arc, or the peak of this arc, and disinfect our system and our water using monochloramines. One of the advantages to that is that the disinfection byproducts. You don't get disinfection byproducts using monochloramine as you would using chlorine and maintaining a free chlorine residual. That breakpoint chlorination is heavily practiced and it works. But in some systems, it may be more advantageous to chloraminate the water because there might be a concern with disinfection byproducts, DBPs. This is, for the people watching this video, Breakpoint Chlorination. You've seen this in a previous video, I hope. And now that which is available on YouTube. And this is just taking it a step further. Any questions on chloramination? Okay, so we're gonna do we have a sample here, sample of water. This is a sample cell. You see it's clean. It's got the diamond right here. This is the chlorometer or color meter for chlorine. Low range, high range. We're gonna do low range. What happens is inside of here, and you want to keep it clean of dust and things like that. But you see where this arrow is, that's where the diamond lines up. Goes in just like that. Now because this sensor in here shoots a beam of light through here, you want to keep it closed. You want to keep that dark. You don't want to leave this meter out, especially if you're out in the field, out in the sunlight. You don't want to leave that exposed because the sunlight can stain or cause the light beam that goes through there not to work correctly. So I have a sample cell. Oh, and I also have 2 DPT packets, DPD, one for free chlorine, one for total chlorine. So we're going to check this sample to see what the free chlorine residual is, and then check it for total. If we take the total, subtract the free, we should get a combined chlorine residual. So we're going to start by, now this is a brand new sample cell, but ideally we would take it to where we pull our sample and we would flush it out. For the sake of this video, we're just going to go ahead and pretend that we've already done that. Now, fill the sample cell to that line, and I look because in these sample cells there will be a slight meniscus. That is, a meniscus is when it's that curvature of the water. At the edges, it's going to be higher than it is in the middle. And you want the bottom of the meniscus to be at that line. Now I'm going to take some laboratory tissue. This tissue will not scratch the plastic or glass sample cell. And it's good to have an extra supply of these sample cells around because they do get scratched after a while. So I'm going to set that in there, and I'm going to calibrate this sample. So it's going to come up all 0. Okay. Take this off, take this out. Now I'm going to start with free chlorine residual. Here's the DPD packet. Give it a few flicks there. Tear it off. And I like to squeeze it just like this. Give myself a little spout there. Way to pour it in. Well, you see a reaction right away. You see that there is a chlorine residual, a free chlorine residual. Now, with a free chlorine residual, you want to give it a slight mix. You don't want to shake it. You rotate it. Rotate it just like this. Don't worry about the reagent that doesn't dissolve. it's not going to interfere with the test. I'm going to clean off the sample cell again. I want it nice and clean. I don't want any bubbles. That's why I'm not shaking it. You see it's nice and clear. No bubbles. I'll set it down with the diamond at the arrow. And you, free chlorine residual, you want to do that within a minute. And I hit the green button. Now we have a 1.11 free chlorine residual. Take that off. Move this. Now, if I set it there and leave it that way, it's going to continue to react. And it's going to get darker. But that's okay because we're done with it. We've got a free chlorine residual of 1.11. I got a good level there. Now, I'm going to go ahead and calibrate the meter again. Zero it out. Get that covered up. Now, this is a total chlorine, DPD. And we're going to let this one cook for about 3 minutes. Those are the instructions from the manufacturer. We're going to follow their procedure. Boy, we saw a reaction right away, didn't we?
Yes, sir.
Start. There we go. We're going to give that 3 minutes to cook, to react. So lately in our training program, in the most recent videos that we did, it's on breakpoint chlorination and chloramination. And a big part of breakpoint chlorination is to determine your total chlorine residual, your free chlorine residual, to calculate out combined residual. You know, we talked about the initial dose when you're determining what your breakpoint is. The initial dose of chlorine reacts with the metals in the water, oxidizes them, and that's why you don't get a residual right away. But then, as you increase the dose and give it more time, that's when you form chloramines. And as you increase the dose, it'll destroy the chloramines. You'll reach your breakpoint, but you won't know that until you can get a free chlorine residual. See how this one's still reacting? Look at the difference there. That's the free chlorine. A 1.11 residual is pretty good. You know, it's below the 4.0 MCL for free chlorine. Well, for free chlorine, that's below the 4.0, the MCL, the maximum contaminant level. So in our system, we should have combined residual as well. Now in our system, we draw from groundwater, our groundwater supply, but that doesn't mean there can't be a little bit of something organic in there that chlorine is combining with. It's probably going to be really close. I would expect that we're not going to have much in the way of combined residual, but we'll see. So we're actually at a wastewater treatment plant. These videos, all of these videos, for the most part, are good for water operators and wastewater treatment plant operators or collection system operators. We've been focusing lately on distribution because that's my crew. My crew does distribution and collections. So we're getting everybody ready to recertify up, get a higher grade. And we'll go ahead. 2, 1, 0, stop that. see what the total residual 1.28. So if you take 1.28 total chlorine residual, subtract the free chlorine residual of 1.11 milligrams per liter, you end up with 0.17. So our combined residual, that is chloramines, is 0.17 milligrams per liter, and that's what we expect, because our source water is groundwater. It's not known for having bacteria and organics in it. You're gonna have something. I appreciate your help. Thank you. Breakpoint chlorination. Let's get started. Number one, as the temperature of the water decreases, the disinfecting action of the chlorine is, Brian, let's start with you.
It's gonna go less effective. C.
Less effective. So if anybody's watching this video, they've seen any of my other videos, they know that chemical reactions when the water is cold slows down. When temperatures are cold, chemical reactions slow down, typically. As temperature rises, as the water warms up, chemical reactions increase. This is especially true with chlorine. Okay. Now pH has an effect on chlorine, its effectiveness, but read the study guide. Number two, free chlorine combines with water to form
B. Hypochlorous acid, hypochloric acid.
hypochlorous acid and hydrochloric acid. Very true. Yep. And under a certain pH, it'll form hypochlorite ions. When the water's cold, it takes more chlorine and more of that hypochlorous acid to disinfect the water. Number three, if the chlorine dose is 5.45 milligrams per liter, a little bit of math. The chlorine dose is 5.45 milligrams per liter, and the chlorine residual is 1.2 milligrams per liter. What is the chlorine demand?
Chlorine demand is C, 4.25 milligrams a liter.
And that is milligrams per liter. Now, chlorine dose. Chlorine dose is, so the water is going to contain organics. It's going to contain dissolved metals, dissolved gases, depending on our source water. So surface water, Brian, is surface water going to have a lot of organics, or is it going to have more dissolved minerals, dissolved gases?
No, you're gonna have more organics in it.
In surface water.
Mhm.
And that's because the surface water is exposed to the flora and fauna of the environment.
Yeah.
Right? A bird flies over the river that we're drawing water from and poops. It's gonna go.
That's organics.
You have fish, plants, people play in the water, all kinds of things happen in the water. All that stuff gets brought into the intakes into a surface water treatment plant. So you're gonna have organics. You're gonna have bacteria, viruses. You're gonna have fecal matter, all that stuff that gets found in the water, in the lake, at the river, things like that. It's all gonna be in the water. So the surface water treatment plant is designed to first screen off a bunch of that stuff, but also settle it out, and then send the water through filtration all the way to disinfection. If it's a water utility like ours, we get our water from groundwater. That's our source water supply. So the source water or the groundwater, what characteristics is that going to have? Is it going to have a problem with bacteria?
No, you're gonna have more minerals in it, hardness, turbid,
Less turbid.
less turbid.
Yeah, because remember, groundwater comes out pretty clear. There's not really any turbidity in the groundwater.
Like more
What causes the hardness?
Hardness is groundwater
Okay.
because of the dissolved minerals. Right?
Gotcha.
Dissolved minerals, dissolved gases. So there's pockets of gas, there's deposits of minerals down below us in the strata below us where the water flows through all that permeable material.
And it's gonna pick up on some of those mineral deposits. It's gonna pick up on those gaseous deposits.
It also picks up what the farmers put down.
Yeah, what gets leached down through the soil, down to the groundwater, yeah, and that's a problem that we have out here, right? Because
Yeah.
historically, this area,
It was all farms.
you know, I was born and raised not too far away from here. And we used to come out here, back in those days, it took like an hour to get out here.
Still does.
Well, now it still
I was
does,
gonna
but that's
say,
only because it's
right.
bumper to bumper traffic and 2 roads in, right? This is one of the fastest growing areas in the United States, and it has been for several years. We got a lot more traffic than we do road.
I was gonna say that's because when he was young, there was no cars.
I was horse and buggy.
Wow, you're way older than me. I'm 55, by the way. Dave is like 82. He still has a sense of humor.
I can't
But-
believe I'm older than Bert.
Yeah, so it was either desert out here or it was farmland. And back in those days, back in the 70s, 60s, 50s, 60s, 70s, farmland out here, you know, hey, if a little bit of fertilizer is good, more is better, right?
Yeah.
Not necessarily. The plants can only take up so much. The plants can only take up so much nutrients, and then the rest of the nutrients gets washed down, flushed down, leached down into the ground. Eventually makes it to the groundwater supply, and that's why we have wells that produce pretty good nitrates,
Yeah.
pretty high nitrates, right? And that's not so great,
No.
because nitrates, if they're,
Me, it is.
well, it depends on what you're using it for. If you're using it to irrigate crops, it's great, it's not
If
a
your job
problem.
is running an ion exchange,
If your job is running an ion exchange, if your job is running an industrial sized water softener,
yeah.
then it's a great job to have, right? But no, but if our customers, the customers it affects, or the people it affects, is babies, toddlers,
And old
babies,
people.
and pregnant women. Because nitrate inhibits their ability to take up oxygen. Oh yeah, sorry Terry. Terry, if you're watching this video, I'll call you later. It's alright. He's a contractor that works for the developer. He can wait a minute. He's a good guy though. Well, he's good to me because I yell at him once. Takes a lot to get me to yell at somebody, right? So, because of the constituents in the water, we're always gonna put more chlorine in the water than is needed to disinfect the water. So we're gonna add a little bit more of chlorine, because we know a lot of it's gonna get used up. We don't wanna just dump a ton of chlorine in there, because that's not efficient. Our second job as an operator is to be efficient. And efficiency means that we don't wanna put too little chlorine into the water to disinfect it, because then it's not doing the job. We don't wanna put too much in there, because it's a waste of chlorine. If you have a lot of extra chlorine in the water, that's not necessary. We've just wasted a bunch of money that belongs to our ratepayers. We don't want to raise rates. Raising rates suck. We don't actually make more money. And that's what people don't understand, is that, you know, in Arizona, we have the Arizona Corporation Commission, and they determine how much money we get to keep of the profit that's made, how much gets invested back, and if rate is gonna go up or down. You know, we've invested a lot of money into this system, but we don't want to spend money arbitrarily. We don't want to over-chlorinate the water. And one of the reasons is because there's a limit to how much chlorine can be in the water at any given point in the distribution system. From the EPDS all the way to the furthest point in the distribution system, the maximum amount of chlorine that can be in the water is 4 parts per million. So that's the MCL, that's the regulatory limit, 4 parts per million. If it's at if it's above 4 parts per million, and we've seen this before, what do? We rush out there and flush.
Flushing.
We get that water out of the system. Well, we didn't actually do that. Never mind. So, yeah, if we're getting close to that 4, we're gonna go out there and flush. You know, if there's a problem with a piece of equipment, we're gonna go out and flush. Okay. So the amount of chlorine that we put in the water is the dose. That chlorine immediately starts reacting with substances in the water that it wants to react with, and chlorine wants to react with almost everything. Chlorine's gonna start attacking the organics that are in the water, the chemicals that are in the water, the metals that are in the water, the gases that are in the water. It's gonna attack it, reduce it, oxidize it, and as it's doing that, the chlorine is getting used up. For every part per million of ammonia, it takes 10 parts per million of chlorine to oxidize it. So even though we're using relatively small amounts of chlorine to disinfect the water, it can get used up pretty quickly. So we call that the demand. We dose the water with chlorine. The chlorine that gets used up is the demand. The chlorine that's left over, is the residual. That's the residual chlorine. And we can measure that. We have ways of measuring it. And we're gonna go into that in more detail. Number 4, milligrams per liter is the same as?
That is C, ppm or parts per million.
Very good. Have you ever heard that question before?
No.
Seems like almost every one of these lectures it comes up, and there's a reason why. It's very important. It's very important for operators to know this information.
It was in the last one, wasn't
It was in the last one, yes, it sure was. Number 5, which of the compounds listed below will raise the pH of water?
C, sodium hypochlorite.
Sodium hypochlorite. So, chlorine gas. Chlorine gas, as it hits water, mixes with the water and creates an acid that lowers the pH. Calcium hypochlorite and sodium hypochlorite mix with water, creates a chemical that raises the pH slightly.
So all your solids and gases, as far as ACL goes, will raise it, except for
The
gas
gas,
form.
the gaseous
Lowers it.
form lowers the pH.
Okay.
Number 6, I didn't even touch it that time, and it changed
That's
on
it.
me. Number 6, new drinking water regulations do not permit the discharge of water with a free chlorine residuals which exceed
That's gonna be 4 milligrams per liter.
4 milligrams per liter. That's the MCL, maximum contaminant level. Number 7, chlorine plus nitrogen equals
D, both B and C.
both B and C, trichloride and trichloramine. Trichloride and trichloramine. Number 8, at a water treatment plant which disinfects with sodium hypochlorite, an operator observes reaction times have slowed during higher concentrations and longer contact times to achieve proper residuals. This is likely due to
A, colder temperatures.
colder temperatures. Very familiar question that gets asked a different way on each certification exam. Number 9, this occurs when any addition of chlorine to the water results in forming only free residual chlorine. Over here.
That is C, breakpoint.
Breakpoint. So what is breakpoint? We're gonna go over that. There's gonna be another clip to this video, and I'm gonna go over breakpoint. In fact, I think the people watching this are gonna see it before you guys get to see it. Number 10, which of the following has the greatest disinfection potential?
A, HOCI.
CL.
CL.
HOCl, hypochlorous acid. The greatest disinfection potential. Number 11, why is testing for chlorine residuals necessary, Brian?
That's gonna be all of them.
All of them. Achieve breakpoint chlorination. B, to confirm a minimum free chlorine residual of 0.2 milligrams per liter in the distribution system. And C, to avoid exceeding the MCL of 4 milligrams per liter of free chlorine. Number 12, free chlorine residuals can be achieved
C, after the demand has been satisfied.
after the demand has been satisfied. Number 13, a method of measuring the chlorine residual in water by comparing a developed color with color standards.
C, DPD.
DPD. Very good. 14, chlorine gas, when mixed with water, tends to,
A, lower pH.
it lowers pH. Very good. Number 15, which is the most effective disinfectant for inactivating bacteria?
B. Hypochlorous acid.
Very good. Hypochlorous acid. 16, free chlorine will react with ammonia to form
It's gonna be your chloramines.
chloramines.
See,
So anytime chlorine encounters ammonia, the first thing it does is combines with it. Combines and forms chloramines. Chloramines are monochloramines. That's one atom of chlorine. Dichloramines, 2 atoms of chlorine. And trichloramines or trichloride, 3 atoms of chlorine. So through the breakpoint curve, as we're building up the combined residual, it's because when we add chlorine, it starts interacting with the chloramines and creating those, or excuse me, with ammonia and creating chloramines. It reaches a point with, as we increase the dose over time, we start destroying those chloramines down to a certain point. We don't ever destroy them all, really. And one of the reasons why we don't want to is because they're a weak disinfectant, but they last a long time. So they last a long time in the distribution system. Now, as we start destroying these chloramines, we get to a point over time with an increase of dose where suddenly every time we increase the dose of chlorine a little bit, the free chlorine residual goes up in the same proportion. That's when we know that we've achieved breakpoint. We've achieved breakpoint when every time we increase the dose a little bit, the free chlorine residual, after that contact time, after about 20 minutes or so, we see an immediate rise in the free chlorine residual. That matches the dose, the increase in the dose, okay? So, number 17, the sum of the free chlorine residual and combined chlorine residual in water,
Is D, total residual.
total residual. And that's it. Thank you, fellas. I appreciate
No,
it.
thank you.
For this last page right here.
We'll get together and go over the breakpoint curve. Probably be tomorrow. It shouldn't take very long, but I want to make sure that everybody gets to see it. And in the video, you should be ready. Let me get back with you. You'll see, folks that are watching the video, you'll see it at the beginning, or near the beginning, along with an example of using DPD to check for chlorine residuals.
Can you call me again tomorrow?
I might. Are you gonna share your lunch with me?